Hello everyone. Today we will be looking at inverse trigonometric functions. Okay, the topics we're going to be covering today. We will first develop the properties of the 6 inverse trigonometric functions and then learn to differentiate these inverse trigonometric functions. First of all, we talk about elementary functions. These are functions which can be algebraic or transcendental. They are polynomial rational functions with radicals. These are algebraic functions. The logarithmic, exponential, trigonometric, and inverse trigonometric functions are transcendental functions. So when we have been, if you remember, we have been solving a lot of problems which can be of either of these kinds, except the inverse trigonometric functions we have not yet done. So this session, we will be talking about inverse trigonometric functions and its differentials. So let's do a quick recap of the trigonometric and their inverse trigonometric functions. Let's start with the graph of a sine function. Now clearly, sine functions, or rather all trigonometric functions, are periodic functions. So for a sine function, clearly the domain is minus infinity to infinity, the range is minus 1 to 1. Now if you want to find the inverse of the sine function, we know any function to have an inverse, it should pass the horizontal line test. So if we draw the horizontal line, what happens? It's not passing. It's actually passing more than 1 point. So that means this function is not going to have an inverse. Hey, there's an idea. We restrict the domain. So that's the idea. So let's restrict the domain of the function. So when we restrict the domain, suppose we're restricting the domain from minus pi half. So if we restrict the domain from here. So let's restrict the domain from here to here. So minus pi half to pi half. So it's just one of the domains. You could have picked up other domain. I just wanted to pick up which is the convention we basically will be using here. So minus pi halves to pi halves. So clearly in that time, the horizontal line only crosses at 1 point. So that means the restricted domain has an inverse function for the sine. And that's the graph of the inverse sine function. Now, the terminology for a sine inverse is arc sine. We are so used to saying sine inverse, but the proper mathematical term, remember, is arc sine x. So you can go back and forth between the two, whichever makes you comfortable. But you'll always remember, if you see the word arc in front of a sine, that means you're having a sine inverse function. So in this one, the domain is minus 1 to 1. The range is minus pi half to pi half. Remember, the inverse functions, they flip the domain and range of the original function. So that's what's going on. Okay. Now, there's some little note here. None of these 6 basic trigonometric functions, as I said earlier, has an inverse if you look at the function on its entirely with its domains and ranges. Because these functions are periodic, remember that. And hence not 1 to 1, that means horizontal line test is not passing. But if we restrict the domains, then we'll have an inverse on the restricted domains. Here is the graph of these 6 inverse trigonometric functions. Just to give you an idea, this is just a recap of your pre-calculus days, guys. Okay, so the main scenario for us and most important for us is the differentials. So I just want you to have an idea of what the graphs look like. So like the y equal to the arc sine, that is y equal sine inverse function. This is the arc cosine function. This is the arc tangent function. Y equals arc secant, arc cosecant, and y equals arc cotangent functions. Then this is the proper definition of the inverse trigonometric functions. We say y equals arc sine of x if and only if sine y equals x. That means if you remove the arc here and take the sine in front of y, that's y equals sine x is the same as sine y equals x. In a similar fashion, y equals arc cosine x is this if and only if cosine y equals x, provided these are the domains. Very, very important. The domains are and the ranges are fixed. And the rest of these trigonometric functions also operate in the same manner. As I said, we are looking towards the derivatives. And this is very important. So here, if you have a differentiable function of x, so this is what literally when you will be doing problems, you'll have this slide in front of you and keep on doing problems based on it. So the differential of arc sine u is u prime over square root 1 minus u square of the differential of arc cosine u, remember u is a differentiable function of x, is minus u prime over square root of 1 minus u square. Differential of arc tangent u is u prime over 1 plus u square. And differential of arc cotangent is negative u prime over 1 plus u square. Notice tangent and cotangent, the difference is negative. Sine and cosine, the difference is of a negative. The expression, everything is the same. And that would exactly follow for the secant and cosecant functions too. Arc secant and arc cosecant, sorry. So the differential of arc secant u is u prime absolute value of u square root of u square minus 1. And arc cosecant u is negative u prime over absolute value of u square root of u square minus 1. So this is the most important slide for us in this section. Now what we're going to do? We are going to do examples. Lots and lots of them. Let's look at the first one. The differential of arc sine 2x. So, and then arc tangent. What I'm going to do is write the differential formula here. d dx of arc sine u is u prime over square root 1 minus u square, and the differential of arc tangent u, keeping in mind my u is a differentiable function of x, u prime over 1 plus u square. So now let's go ahead and apply this to the problem. Now, arc sine u. What is my u? My u is 2x. And then just go ahead and apply the right-hand side. So this is going to be u prime. That means 2x prime differential of square root 1 minus 2x the square. And just now solve, which is 2 over square root 1 minus 4x squared. And you're done. Now let's look at the differential of arc tangent 3x. Now here, your 3x is u. So keeping the right hand side of the equal on the formula, u prime is what? 3x differential 1 plus 3x the whole square. You got to simplify. So 3 over 1 plus 9x squared. And we are done. Now let's look at the next set of examples. Okay, so one has a sine, one has a secant. Let's go back and write down the formulas in the front. d dx of arc sine u, use a differentiable function of x, is u prime square root 1 minus u square. And for this one, the differential is of arc secant u is u prime over absolute value of u square root u square minus 1. Now let's begin with this one. So my u is square root x. So when I take the differential, what do I have? Square root x differential over square root 1 minus square root x the whole square. Now square root x differential means what? X to the power half differential. which is 1 over 2 x to the power, 1 over 2 x to the power negative half over square root 1 minus x. Or you can write this as 1 over 2, can take the square root down and 2 also down, square root x times square root 1 minus x. Okay, you can do further algebra if you want, and the further final answer, because you can take the x inside, 2 square root x minus x squared. Okay, now let's look at the differential of arc secant e to the power 2x. This is going to be, u is your e to the power 2x, e to the power 2x prime, differential absolute value of e to the power 2x times square root e to the power 2x the whole square minus 1. Now remember, exponential functions are always positive functions. Okay, that means e to the power x is always positive, remember that. So that's why I can just simply write e to the power 2x. This one will be square root e to the power 4x minus 1, because it's a multiplication. Now differential of e to the power 2x, chain rule, e to the power 2x into differential of 2x, which is 2, which I can write in the front. Now notice e to the power 2x is common. You can do the simplification. You can easily see that. What do we get? The final answer, 2 over square root e to the power 4x minus 1. Okay, now we are having functions. We will be doing, guys, it's ddx of sine of u first. Okay, so it is ddx of first function, if I think of this as, say, t, okay? Or sorry, not t, or say, let's say a star. So it's a ddx of sine star, where star is a function of x. So that means simply cosine star, okay, times star differential. So let's write that down. First is cosine of arc cosine x, okay, times differential of arc cosine x. Okay, now ddx of arc cosine x, what is it? Let's write this one down here. We know that ddx of arc cosine x is minus u prime over square root 1 minus u square. Okay, so when we substitute, what we get? Cosine arc cosine x times your x is what? 1. So x is, u, and u prime is 1. So that's negative 1 over square root 1 minus x squared. Okay. Now, here the differential is a product of two functions, x cubed, then arc tangent. So, we're going to take the product rule first. Differential of x cubed times arc tangent e to the power x plus plus here x cubed differential of arc tangent e to the power x. Okay, now differential of, remember, of arc tangent u is u prime over 1 plus u square. So let's now come back here. X cubed is what? 3x squared times arc tangent e to the power x plus x cubed, now e to the power x is u prime, times e to the power x differential over 1 plus e to the power x squared. So your final answer, 3x squared arc tangent e to the power x plus x cubed times e to the power x is e to the power x differential is the same, 1 plus e to the power 2x. Okay, let's look at another differentials. Here we have a function 2x times arc minus 2 over square root 1 over minus x squared. So we'll take this function and this function. Here there's a product rule, here's a normal differentials. So if you do f prime of x, so this will be 2, this is the first function and the second function. So a differential of x times arc cosine x plus 2x differential of arc cosine x, and then minus 2, now differential of square root of 1 minus x squared. We all know it is 1 over 2 square root 1 minus x squared. Differential of inside part 1 minus x squared, remember chain rule, is minus 2x. So what we get? So we have x prime here, which is 1, 2 arc cosine x. Now arc cosine x, which is the normal, is differential, so let's write it down, differential of arc cosine x. Arc's u, we use a function of x, is minus u prime square root 1 minus u squared. So x differential is 1, so it's going to be negative 1 over square root 1 minus x is u, remember, x squared. Times, now minus with the minus is positive, and 2x over square root 1 minus x squared. Okay, notice this 2x and this 2 expression cancel out because they are negatives of each other. So what is our final answer? 2 arc cosine x. Okay, let's do one more problem. Once again, you have a function x times arc tangent x minus 1/4 natural log of 1 plus 4x squared. So this expression and this expression. This is a product rule, remember. Now f prime of x is going to be x okay, so x, then you're going to take the differential of x prime arc tangent x. So remember it's the product rule first, plus x times differential of arc tangent x. Oh, sorry, this one, not this one. And then you take the differential of minus 1/4 natural log expression. So minus 1/4, differential of this is going to be 1 over 1 plus 4x squared, and the differential of 1 plus 4x squared. Okay, let's do that. So this is now x prime is 1 arc of tangent x plus x times. Now remember, differential of arc tangent x is now remember, so ddx of arc tangent x tangent u. Remember that. It's u prime 1 plus u squared now. So it's going to be times 1, because differential of x is u is x, 1 plus x squared minus 1/4. Differential of 4x squared is 8x times 8x over 1 plus 4x squared. So 4 goes this. So your final answer is arc tangent x plus x over 1 plus x squared and minus 2x over 1 plus 4x squared. Okay, so we can, gather these terms together. We have arc tangent x minus x, because x minus 2a. Oh, no, we can't do that. No, not possible. Sorry, didn't realize it. So this is the final answer. Didn't realize this was 4x squared and this was x squared. So guys, we are done here. And now it's time for practice problems. So here are a bunch of practice problems for guys you to do. Thank you.